We're solving for non-homogeneous differential equations. And we use a technique called undetermined coefficients. I don't know if you guys realized that or if I said that last time, but our undetermined coefficients method was a little restrictive. This says undetermined coefficients. I don't know. Maybe I should have just typed it. You know, I should make use of this a little bit more. All right, see what we can do. Let's get rid of the other one. That's typed up. Get a little bit bigger. Whoops. Anyways, what I wanted to say with undetermined coefficients is that we were a little bit restrictive with our f of x to just be some polynomial, some exponential function, and some sine or cosine. So we were a little restrictive. I mean, it was easy, right? Was it easy? What? Well, if we try to do like an ln function, for example, then finding using undetermined coefficient wouldn't work so well. You could try it, I suppose. I don't know. I don't know if I've ever tried it. I think I just believe the book. Maybe you should try it. But anyways, if we have a function that doesn't fall into one of these families, then we're kind of unable to solve using undetermined coefficients. So we're going to use another technique called variation of parameters. Now, the reason why we're not initially using variation of parameters using these functions is because it's a little bit more complicated, involves a little bit more theory, and involves a little bit more computation. So if you had a choice, if you have one of these functions for your non-homogeneous differential equations, then you'd probably want to go with undetermined coefficients. And then if you have a right-hand side of your non-homogeneous to be something that's not one of these four families of functions, then you might want to go to the variation of parameters. So what is a variation of parameters? Like before, we start off by computing the solution to the homogeneous differential equation to find our set, our fundamental set. And then remember the Wronskian? The Wronskian for us was a way to determine if functions were linearly independent. And so we introduced that, and you might have done some homework using the Wronskian, but we didn't really do too much with it. And so now we're going to do the Wronskian. So the Wronskian, we're not checking for linear independence because we know that these two, the y1 and y2 from the homogeneous solution, we know that those two functions are linearly independent already. And so what we are going to come up with is the function that we get from the determinant of the Wronskian. So when we get that, we're going to construct two more determinants, two more Wronskians. One of them is we're going to put 0 and fx on the first column and leave the second column the same for your original w. The second one, we'll put 0 fx on the second column and leave the first one the same.
Why? Why are we constructing these ones? They don't understand what's going on.
I think it stands for Wronskian.
Stands for
Do you guys remember, well, what's it called? Kramers Rule. Do you guys know Kramers Rule?
like Cosmo Kramer?
No, Kramers Rule. All right, let's do a little diversion to Kramers Rule.
Cañada Rule?
Yeah, Crammer. Or maybe it's just one M.
I'm not worried about
It's Kramer. Yeah, if you're in the linear algebra class, you're going to hear the same thing again because we are going to talk about Kramers Rule. Anyways, Kramers Rule says that the determinant what does it say? I forgot what it says. The determinant of a 2 by 2 matrix is, well, that's not what Kramers Rule is. So the determinant of 2 by 2 matrix is equal to AD minus BC. Sometimes they call this delta for determinant. So the determinant of a 2 by 2 matrix looks like this. It's the diagonal minus the wings. And if you have a system, AX plus BY equals, let's call it, I can't call it C because that's my next one, DY. Let's call it X, no, I can't call it. C1, no. Well, there's a C here already. Y, Z1 and Z2. Anyways, should have been more careful with my numbers or letters. Then you can find a solution to this. Solutions are given by the determinant times, I'm going to put a straight line as opposed to the square brackets to say determinant. Now this is going to be this original matrix. I'm going to write it down, but I'm going to erase, so you might hold off on writing A, B, C, D. So Kramers Rule says that we're to find the solutions for x1 or x and y, that you're going to find the determinant and divide by the determinant, and then these values in the first column where x is will be replaced by your right hand side z1 and z2. And then your y is essentially the same thing, except the second column will be replaced by z1 and z2. Should have been green. No. So this allows us to solve for a system of linear equations, essentially. All right. So now our problem here that we have what do we have? Y double prime, AY double prime plus BY prime plus cy equals to fx. And then so far we know that y sub c, which is equal to c1 y sub 1 of x plus c2 y sub 2 of x is a solution to the homogeneous differential equation. So what they're claiming here is that the particular solution is actually going to be not exactly a linear combination of these things, but u1 of x, y1 of x plus u2 of x, y2 of x. That this is a solution to the non-homogeneous differential equation. Why are they saying that? I don't know if I know why they're saying that. I don't remember. And I think I can't remember the arguments from here anymore. So anyways, this is the other end of it, and somewhere it would connect to Kramers Rule again. Oh, I suppose we can look at the book. I don't know what page it is. No, it'll be variations of parameter. This is how they justify that the oh yeah, it gets really complicated. So anyways, why don't I just copy this? We have the solution, given the particular solution to be of this form, and then what they do is they take the derivative once and twice so they can put it back to the original differential equation. And when they do that, they get this whole thing to equal to it looks like a first order differential equation with respect to, they kind of fiddle around and change the function, and they're saying that this whole thing now is the function. It's the differential equation where that whole function put together is our dependent variable. So anyways, if these two things are supposed to equal to fx, then that must mean that a couple of these things are equal to fx. So they come up with a system of linear equations that looks like this. And with that system of linear equations, they use Kramers rule to solve for it. So that's the connection. So I can copy and paste this in our notes.
I just accepted.
That's what I say.
You know why there's two W's, right?
What?
Because one of them stands for wonderful, and the other one stands for wizard.
Wonderful wizard. Sub 1 and sub 2. All right, so let's go back to, well, this is going to lead back to Kramers rule, where we solve for U1 and U2, or actually U1 prime. So we have to pretend that Y is like the variable, or is the parameter. So we're solving for U1 prime and U2 prime.
Let's just cross off the book and change the book to like what we're doing. Or is this going along with what
It's going along what we're doing. So this is what we're solving for, and then so this is where we get W is, or the matrix that we're looking for is Y1, Y2, Y1 prime, Y2 prime. Well, it's like U1 prime and U2 prime is the vector that you're solving for, and then this is equal to the right-hand side, which is 0 and fx. So if you tie this into Kramers rule, this is like x and y. This is like x and y. This is like A, B, C, D. And this is what we ended up calling Z1 and Z2. And then so you got the x is equal to this matrix, except the first column with 0 and fx, except instead of x, we're calling it U1 prime. It's 1 over the determinant, and then times the determinant of the y's, the y matrix, except the first column is exchanged with the right-hand side. And then U2 prime is like your y, and it's 1 over the determinant, and then y1 prime, and 0 fx for the second column. And of course the determinant is equal to the determinant of y1, y2, y1 prime, y2 prime, which is what we call the Wronskian. Yeah, so that's how we tie it back up together. And so our task is to find U1 and U2, which means after finding U1 prime and U2 prime, we have to integrate it to get U1 and U2. Okay? So you can see that this is a really involved process, and if I had a choice, I would rather use undetermined coefficients, but that's restricted to those 4 families of functions. So if you don't have that, then you have to use this other method. So let's try a problem. Guess I should switch the order of the notes, huh?
What order?
I don't know. I'll put our first page last right now. So we can pretend that we started off talking about Kramers Rule. And then, oh, maybe I should erase this because this is where I choked. And then we pulled in the book. And then we got this information. And then this is the setup behind it. And then there's one more step after you get your particular solution. You just want to connect that with your homogeneous solution, and that's going to be your final answer. All right. Let's see what we could do. There are some problems here. We want to do secant or tangent first. No, I'm not going to do any hyperbolic functions. Let's try the tangent one and see what happens. This is number 2 from the exercises in the book. This is going to take a whole page here, so. All right, so let's first find our, there's no prime there. Let's first find our homogeneous solution. Oh man, already? Cosine and sine? All right, fine. So m squared plus 1 is equal to 0, so m is equal to plus or minus I. Got conjugates, imaginary numbers, so we're sine and cosine, coefficient is 1. So y sub c is equal to c1 cosine x plus c2 sine x. And we can designate each of these things to be your y1 and y2 when we get into the other part. So that part's easy. That was your quiz, essentially, right? A couple of these things. All right, so now let's get to our fx here. Fx is equal to tangent tan x. So we need a few things. We need our Wronskian. A Wronskian involves the original set of our fundamental solution set. So we got a cosine x and a sine x, and I'm designated my cosine to be y1, so I need to remember that when I solve for u1 and u2. And then the derivatives. Derivative cosine is negative sine, derivative sine is positive cosine. And then we got cosine plus sine, or cosine squared plus sine squared. We have a Wronskian of 1. That's nice. Should maybe put cosine squared x minus negative sine squared x. All right, so that's a good start. Now we need Wronskian sub 1, which is, remember, the 1 refers to the column where you're going to replace with 0 and fx. And then the second column stays the same. And then you do the determinant of that, so that's 0 minus, we got sine x and tangent x. So tangent is sine over cosine, so I don't think that'll simplify to anything too nice. Let me put both of these forms here and decide later on how we want to deal with it. So I might use a negative sine x tan x, or if I just use a tan equals sine over cosine, it might be negative sine squared x over cosine x. So that's my W1. My W2, I probably should have split this up into two different places, but I'll write it out like this for now, and next time I'll hope to remember to split it. We got cosine x and negative sine x, so the first column remains the same. W2, the second column changes with 0 and fx, so that's 0 and tan x. We got cosine x tan x minus 0, and the cosines cancel, sine over cosine, so this is just sine x. Okay, so far? Whoops. Just moved it a little bit. Jeez. All right. We are looking now for U1 prime, and that's W1 over W. So fortunately, our initial determinant was that. So I'm going to use maybe the second one because I'm thinking ahead to an integral that I have to do. And if I let U equal to sine x, so no. Yeah?
You can change it to 1 minus cosine, and then one will cancel.
Oh, that would be
and
good.
then
That's
the other
nice.
one will be
Secant or something.
secant, which I wouldn't do it.
So anyways, the 1 over 1 is good news, so we don't have to mess with that too much. We have negative, the sine is 1 minus cosine squared over cosine x. So what do we got? We got a negative secant x minus one of the cosines cancel, cosine x. Well, since we're here, let's continue to work with this side and just find U1 is the antiderivative of the minus secant, what? Is that good? Minus secant x plus cosine x.
I guess we're filling the W. Or it's just one.
It's just one, so that's nice. Remember the antiderivative of secant x? Secant tangent, so minus
That's the derivative.
secant, what?
That's derivative. Secant tangent.
Yeah, so negative ln of secant
Yeah.
x plus tan x. Remember that? Somebody better look that up, because if this is wrong, then we're just going to screw. It's right? Okay, thank you. And then the antiderivative of cosine, is it positive sign or negative sign? Antiderivative is positive, so that's good. Not that it matters. And we'll not worry about the plus c business. All right, we got U1. Good. Let's try U2. This one's easy because W2 is equal to sine, and nothing too fancy here. And we want the antiderivative of that. And I think that's negative cosine. Okay, so we found it. We found U1 and U2. So let's just tack it on to our particular solution. Our particular solution, y sub p, is going to equal to y sub 1. It's negative ln of secant x plus tan x plus sine x And let's multiply that with y1. What's y1? I think we let it equal to cosine x. And then, well, no, so the fundamental solution doesn't involve the C1. So our final general solution will have a C1. And then our second part of the particular solution is cosine x times, so this is u2, and then the y2 is sine x. And so finally, what?
You label the parts of this.
Okay, so the parts are, this is u1, this is y1, and u2, y2. These are ones over here. All right, general solution. We'll go back to our YC, which is C1 cosine x plus C2 sine x plus, and now we just have to rewrite everything over, minus ln secant x plus tan x plus sine x times cosine x, times cosine x plus, I got a minus cosine x sine x. Never works when you rewrite over stuff here. There you go. We're done. That wasn't too bad, was it? Except for the integral of secant, which now you know, and now you'll remember, at least for the next test. Or have it on your sheet of notes. Whatever. Good? Hope it's right. Yeah, that's right. Now, in one of the examples or one of the exercises there, we could also use this for the first four families of functions that we had. Of course, this is a little bit more long-winded, but it might be interesting to compare the solutions. If we use this method instead of the simpler one. I don't know if you want to do that or if you want to try another one that doesn't involve those nice functions. What do you guys want to do? More of this? Is this fun?
Want is the right word, but yeah, I mean, are there?
So, like number 3, for example, is something where, it seems like we could use, but we can try another one where it's cosine squared, because that doesn't fall in the family of 4 functions that we saw. And there's one with exponential divided by x also that looks interesting. Oh, maybe we should take a look at one-year homework assignments. What's that? This is 4.6. Oh, there's also ones with initial conditions. We'll look at number 28. So I think the tricky part are the integrals after you get the Ronskins and then W1, W2 and stuff, and then you get U prime, then you're going to need to integrate. So aside from the long process, but if you write down the steps, as we do a couple more of these, just write down the steps and then hopefully your integral won't be too bad.
So one of them is a trig function squared.
Yeah.
And then the exponentials. What about number 4? 4, 5.
Yeah, so those are good candidates for this.
Oh, like some triple prime.
I'm slowly getting to WebAssign.
It's not your computer's fault.
No.
Still can see it.
4, 6. Oh, there's only 5 problems.
Yeah.
And look, we did one. Actually, oh, this is a
Not quite. That's what I was.
triple prime.
Yeah, the triple prime. So I'm saying number 4 or 5.
From the homework?
Some variation. I would say 4. Yeah, 4 looks like it's got a lot going on. And everybody's the same. They didn't even bother to. There won't be a practice another version because of that. So,
No, they won't.
nope.
I don't know if I want to do 4. It's too scary.
You can do it. We'll get through it together.
Five is something we kind of did already.
Okay, if you think it's going to be something we can do.
2 would be good?
No.
No?
Probably 4 or 5.
All right, fine. Let's do number 4. The tricky part about 4 is that it's not it doesn't have constant coefficients. But I think that's the deal with the variation of parameters, that it could still work without constant coefficients. Let's see. So, yeah, I don't know if we could do this with, I think we might need a little bit more information. Let me check my notes to see if I have more information. No.
We get this while
No, that's not always the case.
They're letting us skip some steps. And they're only positive numbers.
Yeah, so they have this problem here in number 23, so I wonder if we higher order equations is not homogeneous. Yeah, so I guess it'll work. All right, let's try it.
We got the trig functions in there, so we probably had some imaginary numbers. Y1,
Yeah,
Y2.
yeah. The thing that when we start dealing with higher order differential equations, I think one of the important things to remember is that we want to get the leading coefficient or the leading term to have a coefficient of 1. So I'm going to divide everything by x squared. So this is x squared minus 1/4 over x squared y. And I guess more importantly, the right-hand side is going to be so this is going to be the function that we're going to look at, focus on. Right, let me make sure. Method examine homogeneous differential and generalized. Just put it in standard form. It's complementary, then a particular solution is going to be given by this undetermined. So it looks like it should work. All right, let's go at it. So we got fx figured out, and we have these two. So we need the Wronskian. So w is equal to
Y sub c.
x to the 1/2. Y sub c is just a linear combination of these two. I'm not going to write that. Negative 1/2 cosine x, and I'm going to save some room here because I think we're going to need the product rule. Because the second row is going to be the derivatives. So it's the derivative of the first times the second plus the first. I think it's going to be a minus when we take the derivative of the second. So the first derivative of the second, which is sine negative. All right, so that's the first one. Second one, we'll go through the same process. Derivative of the first times the second plus the first and derivative of the second. So the Wronskian is the thing, whatever. So we have to add the powers, right? So this is x to the negative 1/2, x to the negative 3/2, x to the negative 4/2, x to the negative 2. So minus 1/2, x to the negative 2, cosine x sine x, plus x to the negative 1, cosine squared x. So that's the diagonals being multiplied, and we're going to subtract the wings being multiplied. Negative 1/2 x to the negative 2 sine x cosine x minus x to the negative 1 sine squared x. All right, So we're gonna continue to mess around with this, so it might be good to take the time to simplify it. I have these two. Hey, they have opposite signs, right? So one's a positive, the other one's a negative. Everything else looks the same. That's gone. And then we have these two.
Shouldn't be a sine squared.
Yeah, that would make it even nicer. So we can factor out a sine squared because this is a plus. We can factor out an x to the negative 1. I mean, we got sine squared, cosine squared x plus sine squared x. So let me write that out. Times x to the negative 1. So that's just 1 over x. Right? It's not too bad. So that's our Wronskian. Now we need to figure out our W1. Our W1 will have, so this is where the x to the negative 1/2 comes in. And then the second column stays the same. So we have x to the negative 1/2 sine x. And then we have this other big mess over here, but when we find the determinant, it's going to be 0. So let's not worry about that. So it's just 0 minus x to the negative 1/2, x to the negative 1/2 sine x. So this is negative sine x over x.
Is that sine?
Come on. Should I just type everything?
Maybe. I don't know if it's better or worse. There's like a book.
Holy smokes. Are you happy now?
Beautiful.
All right, let's do W2. Again, we have 0 x to the negative 1/2, and the 0, the wings here wouldn't matter because when you multiply it by 0, it'll disappear. So the only thing that would matter is this top part, which is x to the 1/2, x to the negative 1/2 cosine x. And when you multiply it, you get x to the negative 1 cosine x minus 0. So when you put this, when you divide this by 1 over x, the 1 over x will disappear, right? The reciprocal business. So that'll make our integrals a lot easier. Wow, this is going to be easier than I thought. U1 prime is going to be W1 over W. W1 is negative sine x over x divided by 1 over x. That's negative sine x. And then the antiderivative of that is positive cosine x. So we got our U1. Great. U2 prime is W2 over W. Let's just say it's cosine x. And then U2 is antiderivative of cosine x dx, which is positive sine x. I think we got it. So our particular solution will be, I think I do this in purple, y sub p as u1 times x to the negative 1/2 cosine x. That's our first, well, that's our y1 solution, plus u2. I think I might have switch the u and the y's. X to the 1/2 negative sine x. But if we label it, you'll remember this is u1 that we found, this is y1 that was given, u2 that we found, and y2 that was given. So if you just string this up into your final answer, we should get, I don't want to plug it in, it's going to be wrong. Oh yeah. What? Oh yeah. Is that going to work? So it's 1/2 cosine squared x plus, oops, negative sine squared x. So we can factor that out. 1 over square root of x. Wow, okay. All right, let's see if it works. I'm going to have a drum roll or something.
It's just
Make it
asking
sound
for
exciting.
particular?
No, it's asking us for the whole solution.
The general?
Yeah. So the general solution would just have
Some one.
times all this stuff, right?
Okay.
And then any way you want to write this, x to the negative 1/2. Hell, if you didn't simplify it, they should still probably think it's okay. I don't want to hit it. Should I hit it?
Yeah, we got it.
Is there a drum roll?
Boom.
That's right?
Yeah.
Oh, good. Yay. Whew.
Number 5 can't be that bad. Let's do it.
No. I think I'm tired now. How's it look? It's a process, right? Alan, wait. Did you get it? Did you
Take
get
lots of
it?
pictures, take lots of pictures.
Yeah, it's on the video. You could watch the video. It'll also be in the notes. So the process, right? You find the Wronskian, the W, and then you find W1 and W2 by replacing one of the columns. And then after that, you find U prime and U1 prime and U2 prime, and you integrate each of those to find U1 and U2, and then you just tack them along. We only have 5 minutes, so let me start number 5
Okay.
for Brian, since he's always asking. But there's something, well, you could see that it's a third order differential equation, so you're going to have 3. So I'm not going to finish this. Oh, if it's 3 of them, let me look back at the notes.
Yeah.
Oh, 0 and 0. There's a bunch of zeros. All right, so let's go back. We need to find our, what do you call it? Our thing. Auxiliary equations. So m cubed is the third power. There's no m squared. There is an m, and there's no constants. 0 and cosine sine. So we got m is equal to 0 and plus or minus I. And so that would lead us to our y sub 1 to be just a constant 1, e to the 0 power. And y sub 2, whatever you want to do first, sine or cosine, and then y sub 3 to be the other function. So now we have 3 of them. So our Wronskian is going to involve the second derivative. So our w is going to be 1 cosine x sine x. It should be in blue now. And then take the derivative, negative sine x, cosine x. And then take the derivative again. So this is where you have to do the second derivative, because we got higher order derivatives. And so now we have to find the determinant of this. So we didn't really talk much about determinants of 3 by 3, or have we? So here's how you take the determinant of a 3 by 3 function, or 3 by 3 matrix. To take the determinant, you're going to expand over a row or a column, and in this case I'll expand over the first column. And then what happens when you expand over the first column is that the determinant is going to equal to this 1 over here times, and then here you cross out the row and the column in which that element belongs in, and then you have this submatrix, and then you find the determinant of that submatrix. This should be a straight bar. Determinant of minus sine x cosine x minus cosine x minus sine x. Now technically you're not done, but in this case we are, because next you change the sign. So this first one's going to have a plus, the second one's going to have a negative, the third one's going to have a plus. You change the sign, and then you're going to subtract 0 times the determinant of the submatrix after you cross out the row and column in which that belongs in. So that would be, I'm going to write this out even though it's going to be 0 anyways, but it'll be cosine sine negative cosine negative sine. And then technically you got one more to go down here, the last 0, and this will have a plus. So there's this alternating sign business that's happening. It always starts with positive on the upper left-hand corner, yeah. And then after you cross out the row and column in which that belongs in, you're going to have a cosine x sine x, negative cosine x sine x, which again doesn't matter because it's going to be 0. So negative, 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 so this is just going to be 1. So negative sine squared, or positive sine squared plus cosine squared is 1.
How are we still gonna find the one of the,
Yeah, the one.
like reducing the second row and the third row?
No, you only do 1 row, 1 column. So
One.
you can expand because that's how determinant rules are.
No, I mean, aren't you gonna like cross out the second row and the third row?
Oh, yeah, that's how I got these things.
I mean, just regarding columns, but not regarding rows. It's two, because there's supposed to be 9 of them when you calculate.
Oh, but those, yeah, those are cofactors. That's a long way of finding it. So this is expanding through 1 row or 1 column.
So then that 1 times we end up with sine squared minus cosine
Minus
squared.
negative cosine squared.
Or minus negative?
Right.
Subtract them.
Yeah. So let me just write W2 because we're out of time. So it'll keep the first row, it'll keep the last row, or it'll keep the first column, it'll keep the last column. And then this middle column because it's 2, is the one we're going to change to 0, 0 on tangent. Oops, I meant to have that a different color. So based on your fx, the right-hand side, you're going to have 0, 0, and fx for the rows that you're going to fill in for the w sub whatever. So you'll have 3 u's to find, u1, u2, and u3, and then you string them all up in the end. Okay? All right. Good luck with your homework. Whew. Man.
Professor, I don't see why you can work like using your method, just calculating 1 rows. Because aren't we asked to do like 9 of them? 9 2 by 2 determinants.
Well, that's what you would do to find cofactors, but we're not looking for cofactors. We're just expanding through one of the either any of the rows or any of the columns. You just need to expand through one.
I still don't see how.
Yeah, that's the determinant.
So I did it, and it looks like W2 and W3 are the same. Would that be okay?
That would be okay because they're sine and cosine, so that's probably okay.
All right.
Yeah.
And then just plug that in. Cool.
Yeah. Hopefully it works.
Yeah, because as far as by now, the 2 methods I have learned to calculate the determinants. One is the Salute rule. Salute rule. I don't.
Salute.